would like to thank the organizers for the invitation to this place and for the opportunity to give a talk. So, I want to talk on an additivity theorem for cobordism categories, and I would like to start by recalling a theorem from geometric topology. Genauer. So, to formulate it, we need the cobordism category. So, cob D, the cobordism category. So an object is a D minus one dimensional manifold, which is closed, and the morphism is the cobordism between these, and then we can compose by stating cobordism. And then we have to be careful so that there is really a category. But let's assume we can do this. So this is due to relations Nazi-Tim device. And okay, so this is this object of which you can take the classifying space. Now we can do the same construction for manifolds with boundaries. So an object would now be a manifold with boundaries, and a cobordism would be a cobordism between these. So this is a cobordism, which is something like so this should be a manifold with boundary, and this is another manifold with boundary, and there's a cobordism in between. So that's a manifold one dimension higher, whose boundary is decomposed into three parts, like the incoming and the outgoing, and there's some vertical boundary, which is a cobordism between these boundary pieces. Okay, so this is clearly a subcategory of that, because a closed manifold is a complex manifold with boundaries, so the classifying space sitting in here. And now there's a functor from this category to cob T minus 1, that's given by taking the boundaries. So on objects, I would take this boundary piece, and on morphisms, I would take this boundary piece, which is a cobordism. So that's a functor, and it gives it back on classifying spaces, which we call del. And so the theorem is that this is a vibration sequence of spaces. Okay, if you look into Genauer's paper, actually he proves much more. He just determines the homotopy type of this cobordism category in a similar way that the homotopy type of this cobordism category was determined by relations Nazi-Tim and Weiss. So this is an infinite loop space of a certain Tom spectrum, and he proves this is also the infinite loop space of a Tom spectrum, then the suspension spectrum. And then, well, this vibration sequence is just proven by comparing the homotopy types, this Tom spectra, and see that they fit in the vibration sequence.
Is this a recent paper? Or?
No, this is from maybe 10 years ago, something like that. I forgot it. Yeah. It's classic. Okay. So I was interested in giving a proof of the theorem, which did not use the computation of the homotopy type. I mean, we can still, these are purely geometric objects, and we can wonder whether we can prove such a theorem without knowing what the homotopy type this is. And the reason for doing that is that it's quite easy to write down cobordism categories. We can make simple variations of this theme or other stuff. I mean, I'm going to explain it later, some examples. And then we have usually no clue how to compute the homotopy type, unless in special cases maybe. And then maybe we still want to compare at least the homotopy types of these kinds of cobordism categories without actually knowing what they are. Okay, so let me give you an example of such a cobordism theory. Cobordism category. So let's take a category C, maybe infinity category or category. And let's assume it's closed under pullbacks. And from this, we can look at a span category. Span category. And the idea is that a cobordism between two objects of C should be a span. Okay, and then we can compose spans, because we informally break down what a span category is. So, informally, an object would be just an object of C, endomorphism would be a span. So a diagram in C, and then we can compose. Well, if I have a span, and I have maybe another span, then I form the pullback. And this will be my new span. And then, of course, I mean, many of you know that this is an operation which is not so well defined because we have to choose pullbacks. And as a matter of fact, then this is not really a category, but it's an infinity category. We can write down a single space if you like. So let me precisely write down what the span of C should be. So that's a simplicial object. And in degree n, I take the functors from a certain indexing category, which in degree 0 is just a point, in degree 1 is the span, in degree 2 is like this. Well, that's the shape of the index category, and then I call this SDN because it's the edgewise subdivision of the n simplex. And then to C, and then we are not allowed to look at all functors because I said this must be pullback, so we have some pullback condition here, saying all squares must be pullbacks. Yeah, and then we take the groupoid core of this. So I mean, this is a category under natural transformations. And you get a subcategory of isomorphisms. So this is a space, and this defines then the simplicial space. That. And so this is actually something like a category because so Barwick has shown that this is a single space, a complete single space. Okay, so we may do this as some kind of cobordism category, and maybe you can wonder what's the homotopy type of the specifying space. And actually, what Barwick also showed that if C is a stable infinity category, then the loop space of the span category, specifying space and loop space of this is a model for the algebraic K-theory of the stable infinity category C. So that's an object people find interesting and which is usually very hard to compute. Okay. So in this situation, it might be interesting to compare at least.
So was this a definition or?
Well, you can use this as a definition if you like for the K-theory of a stable infinity category, or you might also use an F-dot construction if you like. Find the K-theory of a stable infinity category, then this is a statement.
And I've missed the point how you put actual geometric cobordisms into this now. Why
this
are they put
cobordism is just a word. No, I mean it's
something to do with manifolds.
No, but I mean if you take, for example, C, the category of perfect chain complexes over group ring, over C pi, then if you have manifold, you put this map to be pi. Then this, you can take the cochain complex of the genus cover. This will determine an object here, and the cobordism will determine a span. So we see this is some relation at least. We have a map maybe. But of course, the setup is not
a cobordism category and a span category.
So you don't like, I call this cobordism category, then
well, I asked you if there's anything to do with cobordism, you said no. So
yes, I said there was a map in specific cases. But I used the word cobordism just as a suggestion, I think. I mean, if you don't like it, you needn't do that. But I found it useful to think of these objects as kind of cobordisms. That's all I want to say, yeah?
If you take C to be the infinity category of perfect complexes or something over modules over a ring, you recover the usual K-theory of the ring?
Yes.
And then the span, what's special about a span is just any two maps of complexes.
Yes, so if you look at equivalence Q construction, for example, you always have conditions with empties and monos.
Yeah.
And we don't need this in the infinity category context. Because I mean, our diagrams are coherent on the nodes, so we don't need any cofactorization conditions.
Oh,
okay. So, I mean, part of the message I want to do is that it's useful to think of these objects as kind of cobordisms, so they are not. And of course, if you don't like the term, you just say span. So, let's look what the analogue of Genauer theorem in this context would be if we interpret the cobordism as a span. We can wonder whether such a theorem is also true or not. And to formulate it, well, we know what the cobordism category is. We need to know what cobordisms with boundaries are. So what's a cobordism? Manifold with boundary is a cobordism from something to the empty set. 0 maybe. So let me define the category null C, so the category of null bordisms, objects with boundaries as a subcategory of Q1C. So that should be the full subcategory on objects of the form C, W, contractible. Okay, and so we think of this as an object with boundaries. Q1C, I didn't introduce the notation, sorry. So maybe I call this category QNC, right? So this is the category of n spans. And we take the group I call that. Yeah, sorry. So this is the subcategory of the span category of the category of spans. So an object is span and homomorphism is a natural transformation. And we look at those of this shape. So this is something like an object with boundary, and then the statement would be that K of C, well, this sits in K of null C, because a closed object with boundary, where the boundary is empty. And then we have a boundary functor, which takes such a thing, and that's a boundary piece. And the statement would be that this is a vibration sequence. And actually, that's a true theorem. So this is what's called Waldhausen's additivity theorem. And
so the context here is that C is stable and the K-theory is Waldhausen K-theory, or?
yes, so I should say, so probably if we replace by span, then this is a true statement with just the assumption on span that it's closed in the full base. But okay, we should see stability in category to have this K-theoretic interpretation.
Sorry, how was K of C included in K of null C?
Well, there's a functor from C to null C, which then takes an object C and views it just as a thing without boundary. Okay, and there's a functor from null C to C, which takes an object. So this is contractible and then shifts to the boundary, which is this piece. So it's quite analogous actually. So that's Waldhausen's additivity theorem, and I should say you prove this in this infinity categorical context. So this is due to Barwick and user Caruana. Okay, and now, I mean, this looks very analogous, and now I want to convince you that actually there's a proof which simultaneously proves this statement and this statement, so that this analogy is quite helpful. Okay, so the sketch of that. Proofs of both statements. Yes. So let's maybe look first in this geometric world. So again, we have this functor, which shows T minus 1, boundary functor, and then this cop D is actually the pullback. Right, I mean this is actually the pullback over the empty cobordism category, or the cobordism category containing empty only, because I mean a manifold, closed manifold is a manifold with boundary whose boundary is empty. So that's a pullback of categories, and actually it's a pullback on the level of each nerve. So on, what I want to say, there's the definition. I want to say that it's even a homotopy pullback on each level of the nerve. So on objects, I have a manifold with boundary. I marry to the boundary, and these are all spaces now in the cobordism category. And this restriction to the boundary map is a fibration of spaces. So that's a version of an isotopy extension theory. And the same is true for morphisms.
When you make the cobordism category into spaces, it's all fiberwise oversimplices?
Yes. So I
And
mean,
then
it's a
transversality on
classified
the boundary
space.
or something? Or how do you?
What was the question?
I don't know what the set of manifolds is, and when you look at this as a space, you would
So-
fiberwise oversimplices?
Yes. So it should be a classifying space. So for example, the object space here is a classifying space for manifolds, closed manifolds, bundles of dimension T minus 1, of smooth manifold bundles, whose files are smooth manifold, closed manifolds of dimension T minus 1. And this is similar thing for manifolds with boundaries. topology in the object space is defined in such a way that this is a classifying space. Yeah. So this was defined by Genauer. And it's extremely important to take this topology into account, because otherwise this computation of the homotopy type will be wrong.
Sure, if you make the space discrete, this can screw up on the back.
Okay, so this is a, first of all, it's an actual pullback, and second, on each level of the nerve, it's a homotopy pullback. On each NK. Okay, now sadly it's wrong that if we have a homotopy pullback on each level of the nerve, and we realize it will usually not be a homotopy pullback anymore, so we need some criterion. And so the criterion which we want to use here has to do with Cartesians and co-Cartesian vibrations. So the main step, main ingredient, if you want to show a theorem like this, would be the following. This word, I mean, it's more maybe observation, but I mean, it's quite helpful here. So this boundary functor is a Cartesian and co-Cartesian vibration. Okay, and then under certain circumstances one can show that such a thing induces homotopy pullback after realization. So if these were quasi-categories, then probably maybe people in the room would more proof of respect. Here it's a bit more complicated because we're looking at topological categories, actually, which are non-unital. So we have to name these as non-unital categories, otherwise the statement is wrong. And people sometimes join 3 units to that, but of course this destroys the categorical structure. We should not do this in this context. Non-unital categories, and then we also need to know that it's actually a weakly unital category in the sense that we have something which behaves like an identity under composition. So weakly, that is just right. Weakly unital category.
So what's the Cartesian separation of topological categories?
Want to explain that?
So is this a property of the specific model you have for delta in mind that Genauer wrote down, or is this an invariant property?
I mean, you can write it down so that it becomes an invariant property of semi-zero spaces under level equivalence. So it only depends on the nerve and the level-wise model structure. This answers your question. But I mean, if you want to do that, then you have to be a bit more careful than I am now in writing down what the condition is. Or we will see that. So let me just write down the definition which works. Yeah? So the situation is we have a functor between topological categories, so continuous functor, and these categories might be non-unital. Yeah. So I have to define what a Cartesian morphism is. So morphism F from C to prime is called P Cartesian. So if, let me write this down, so for all test objects P and C, we get, when you look at the morphisms from T to C, category C, and you can post-compose with F, get a morphism from P to C prime, and then we can apply P here, and get a morphism D from PT to PC, and we can apply P here to get a morphism from PT to C prime, and we can also post-compose here with PF. So this is a commutative square, because P is a functor. And the condition is that this is a homotopy pullback. Okay. These are all spaces, and it should be a homotopy pullback of spaces. So what does this mean? Let's try to see what this is. So let's take an element in the pullback. So this is maybe some morphism from T to C prime. Okay. And then we also have our morphism F from C to C prime, which I just write down here. So we have a morphism from T to C prime, and then we project by P to get a morphism from PT to P C prime. And this should factor through PF. So this should factor as PC and PF. This is the condition, and then we claim that there should be essentially a unique morphism from here to here, such that this triangle convolutes, and which lifts this morphism here. I'm not quite. Okay, so that's the Cartesian morphism, and Cartesian fibration is a map where we have enough lifts to Cartesian morphisms. So F is called Cartesian fibration. And if, well, each morphism down below, which I will call prime, B, and each lift of the target through P, so all C prime and C, P of C prime and P prime, there should exist a Cartesian lift C to C prime, F, so it should be lift, and it should be P Cartesian. Okay, so that's the definition. And a co-Cartesian fibration, so this map is a co-Cartesian fibration, it's a, if it's op, it's a Cartesian fibration. Okay.
I mean, this condition 2 is what makes it the way it's stated, not invariant, but it's easy to correct.
Yes, so it's not invariant, you can see we need explicit lifts, but we should try to replace homotopy and stuff like that.
Quality by equivalence in the error category.
So, you're proving a property of this map which has to do with manifolds.
Yeah.
So this is a property of manifolds. What is it? What is this?
Let me explain that now.
Sorry,
Yeah.
what was just before you considered capital F? Was you hadn't used capital F?
Capital F is
P and F.
P, sorry. Thank you. So it's this function. Okay, let me try to explain the proof and then maybe also explain why the same thing is true in this span category setting. Okay, so this is a proof, and maybe just draw pictures. So let me just explain how to find Cartesian lifts. So what's the basic datum? We have a morphism down below, so that's a cobordism. And we have, so maybe this is a cobordism. W, and then we have a lift of the target of n through here, which means I write n as the boundary of something else. So we have a null modism of n. Let's call this x, and then we need to find kind of a universal lift. Yeah. So we need to find something here and something in between. Okay, how do we do that? Well, let me first, so this has some kind of corner here. Let me remove the corner. So I get a picture which maybe looks like this. I have my n, my x, and my w and my m. So this is not just a manifold with boundary. I glue these two cobordisms together. Okay, then I cross everything with I.
What do you mean remove this? Just looks like the same picture.
Yes, probably you're right, but I mean you're gonna understand it. I mean at the moment we have just one cobordism here and another cobordism here.
It's in the corner?
And there's no corner so far. Yes.
You don't mean remove.
So far there's not really a corner, I think. But I mean in this picture it looks like there was a corner and then we straightened the corner.
Remove sounded like you're taking compliments.
Oh no, sorry.
Straight in the corner.
Straight into the corner. Okay. Then I want to take this picture, cross it with a unit interval. So we have, sorry, probably I need a bit more more space. Floor is larger. So we start with this picture here. W and N. Then we straighten the corner. Right? Cross with an equal.
I'm sort of sorry, I have a conceptual problem.
Yeah.
Why was there a corner? You know,
There was no corner. There was no corner. I
Okay,
agree.
so-
There was we just glued the two together.
So it has nothing to do with corners, okay.
Yes, maybe you see it in a minute why this kind of has to do with corners, and it also we have to do something in case there's a tangential structure. Then we cannot just glue them. But the tangential structures don't match, so that we can do in the case there was a tangential structure. And something is rightly like turn. Maybe I should say I turn this around.
But these things are not embedded, so that I try to understand what
They are.
is actually
They are embedded.
They are embedded.
At least one model. Okay.
They actually sort of orthogonally embedded somewhere. Oh, that does make sense.
So I take M, I take everything across the interval. Something like this. Now, okay. So this was W, and this was X, and this was N. And then, now I really introduce corners at this place, and I straighten corners here. Okay, so the new picture looks like this. N, X, then we have this W now here, and then we have some M times I, which maybe just forget. It's a bit longer W, okay? And then we have this picture here, and there's something here, okay? And then we see that precisely something that fits in here. So it's a morphism that projects to this, into this, so that's fine. And then we can prove that it's actually co-Cartesian, a Cartesian lift. Yeah, so why is this true? Well, if we have something, maybe something new cobordism, then we have to factor this new cobordism through this one. But then we introduce the corners again, so we are in this picture, and then we just have to squeeze in M times I, and we can do this in a color. Okay, so that's the proof how this works. And then, I mean, of course, you have to be more careful, but I don't have time to explain this in detail. Okay.
The point is that the underlying manifold is just a color neighborhood of what you had to begin with. So you
Yes.
can embed it anywhere you like.
Yes. And then Stefan wonders what this has to do. I mean, it's a construction of manifolds, but actually, I mean, this looks like a very formal construction which just uses that we can rearrange things. So we could try to do the same thing on diagrams. Okay, and we can.
Yeah, so it seemed like the existence of colors and that the choices of colors are contractible. Is that what makes this work?
I mean, everything here is provided with colors, I should say. From the beginning. Everything is embedded in Rn, and then you have a nice little neighborhood. Otherwise, you cannot even glue two cobordisms to keep together.
Well, in Rn colors can make up the contractible choice.
Yes.
And we're infinite categories anyhow, no?
So maybe you could also write down a model. But I mean, I stick to this model. I mean, this was defined by other authors. Okay. Now, let's try to do the same argument for span of null C to span C. Okay, so we are given now a span in C, so there's something like C, W, G, and I'm giving a D, a null bodism of D. I mean, it's just a span of this kind, and then maybe I forgot the contractible data over there. Okay. And so how do I, now I need to find a Cartesian lift. Well, I do the very same thing. I turn this around, I glue this together. So this is the formula for gluing is I take X times over D W to C. And then I cross with the identity, which is, well, it's quite simple. We just take identity left everywhere. Okay. And then I rearrange the diagram again so that it looks like this. And then, I mean, this stays the same if you don't touch this part. Okay, and then you can show this is a coefficient. at least for me, this analogy was quite helpful because otherwise I don't quite know how to write down the co-partition list, but with this geometric picture, I might.
Where's the x cross w over d in your pictures on the left? Is that the, where's the?
This one?
The first step. The very first step.
This is the gluing of these together.
Yeah, I got that because you straightened it out, but where's the x cross w over d in your left-hand picture? Is it just not there, or? In the diagram, in the category version, you have x cross w over d.
Yes, here.
Where is that in your picture?
That's an algorithm.
The whole thing.
The whole thing. It's gluing together this cobordism from C to W with the other cobordism from W to NT.
Oh.
Or to 0. So that's this here. Okay. So this provides a proof of 5070. Okay. Now I want to convince you that, I mean, so far we have just reproven things that we already know, that we also can get something new out of this idea. And actually I want to refine this very naive picture of a cobordism to something which maybe looks more like a cobordism. So I mean, this idea of this comes from surgery theory, I believe. I mean, the very naive model of a manifold is just a cochain complex, but it's too naive because when the manifold is closed, you have a Poincaré duality structure that in the cochain complex is a Poincaré duality chain complex. And there's a whole Waldhausen theory of that, which refines in some sense this spin chemical stuff, and which was worked out by Ranicki, and was kind of brought into more modern language and not generalized by Jacob. So let me review this theory. So the idea that there's some cobordism theory of J complex with its duality is really, I think, due to Ranicki, and he used this to write down this L theory in spaces. And like the L groups are like the cobordism groups in this theory. And now we want to refine this to a whole cobordism K theory. So let me maybe give you a simple example, which Ranicki, I mean, it's not simple, but I mean the elementary example that Ranicki was interested in. So we take a ring with involution. So what is an n-dimensional Poincaré chain complex? Over R. So well, it's an n-dimensional. It's a chain complex, just a finitely generated projected R chain complex. Think of the cochain complex of a manifold. And then we have some Poincaré duality structure. So what's that? So that's product pairing gives us a bilinear form. So let me write this as a homomorphism from C into its dual, and then maybe up some shift because we are n-dimensional. Okay, so this would be a bilinear form. So it should be R bilinear, and this to write this down, I need R to be a ring with involution because I mean, however, if this is left module, this is a right module, and then you have to use the involution to make this a left module. And geometrically, this involution corresponds to orientation data. The ring is like a group ring. Okay, and then it's not just some bilinear form, it's symmetric. And it's homotopy symmetry, so that's homotopy point. So this is now a symmetric bilinear form, but then of course it should be non-degenerate, so we need a Poincaré condition. So let me call this one Q. So this Q of course has an underlying map, and this should be bilinear form is non-degenerate. Okay, so, and with this you can work. You could also maybe take homotopy orbits here, which is necessary for surgery theory, because the surgery constructions actually take values as a quadratic version of theory.
So when you say that C is a finitely generated projective R chain complex, do you mean like it's finitely generated projective in each degree, or do you
Yes, maybe, or maybe up to.
Okay, so you don't mean that it's projected in the category of chain.
No, it's levelwise projective.
Level.
It only has finitely many levels.
Yeah.
Also.
Yes, up to quasi-equivalence at least, I think.
There's no symmetry condition on the Q?
Well, this is written down here. So homotopy fixed point for the involution.
Ah, okay.
And the involution here precisely corresponds to flipping the two factors.
Okay.
Finding the form. Okay, so Jacobi generalized the setting greatly, and let me explain how this goes. So I think the main observation one makes is that this functor here, the functor which takes C and takes this hom RC, sigma n C dual, homotopy fixed point, it's a quadratic functor in C, in the sense of Goodwill calculus. Okay, and from this actually we can recover everything, so that's quite nice. So general setup. So C is the independent. Then we take a quadratic functor, which you think of in this symmetric bilinear forms. Q is a functor C of spectra, and it's quadratic in the sense. And good for this functor calculus. Okay, then we want to write down what a Poincaré object is, and then maybe you wonder how you can ever do this, because first of all, the Poincaré duality is something not on this homotopy fixed point, but on this underlying factor. So we have just an abstract Q. How do we recover this? But there's a trick for that. This is the polarization. So we can always compare Q of C plus D with, so this contains Q of C plus Q of D as a retract. You can always write down. It's always a symmetric bilinear functor. And if Q is quadratic, then this is bilinear. Okay? And okay, in this situation where we had this functor, then this bilinear functor, this cross effect is just a hom. So that's quite nice. But then, of course, we want to write down an element in hom as an actual map. So we need some kind of dual thing here. But actually, if such a dual thing exists, such that the bilinear thing is a hom, then I mean this is unique because it's representable. So I mean we just require that B, the functor, is representable in the sense that there's some natural equivalence of spectra like this. Okay, so and then I mean we can write down basically this map, I think. And then maybe we need something more. So this is not quite a duality, the star operation, D to D star. To make it really a duality, we need the condition that a certain map which goes from C to the double dual of C, that this is equivalence. So that's not automatic. You can easily cook up examples looking at not finite chain complexes where the double dual is not equivalent to its original object. Okay, so that's the setup, and such a pair CQ we call Poincaré category, and there's a category we call cut P Poincaré category where the objects are just pairs CQ as above. So it's a quadratic functor, and everything is determined by the quadratic functor provided we have some conditions on Q. And then maybe tell you what a morphism is, and with the systemorphism you would get into.
Just reverse that by saying it's the same as category with the duality, since it is.
It's not quite, there's more information than that. I mean, it would be the same, I think, if you would take this example all the time, homotopy fixed points of the hom to the dual. But for example, there's the homotopy orbit construction, that's also a quadratic functor.
Oh, okay.
It's a quadratic refinement of this construction, if you like. So, in general, it's true that any quadratic functor, I mean, this has this bilinear thing, and it's a linear extension of this bilinear thing. So, it's a linear extension of this one, and this might have additional information.
Okay.
Yeah. Okay, homomorphism, well, we just say this in words. It's just, well, it's a functor from C to some other category D, and then we can use this functor to pull back the quadratic form on D and we won't have a map. So it's just a morphism. I mean, it's just some translation category. I forgot some condition. Sorry. That wasn't the case. So let me write down what a morphism is. So a morphism is from C to CQ to C prime to Q prime. Is a morphism in fact functor from C to C prime. And then there's a morphism from we require a morphism from Q to the pulse axis in here. here. And then, I mean, the problem with the dualities is this might not respect the dualities, so we have to impose this condition. Yeah. That respects the dualities in the sense that for each object there's a canonical map on f of the dual to dual of f of c should be equivalence. This is not kind of automatic, and we have to require this. Okay. And using this kind of setup, we can write down what a Poincaré object is. Poincaré object in CQ. Well, it's an object in C, and then some element Q in omega infinity Q of C. So something like this. Okay. And so this always determines now a map as follows. So we can always diagonally let Q of C equal C plus C. And then we can project. I think the definition is gone, but the definition of this bilinear thing was precisely it was a quotient of that. So we can project, and this is the Hom into the dual. And so each element Q in here, in the loop space, gives us an actual morphism from C to C prime in our category, and we write this to be an equivalence. And then we can define here P of CQ is the space of Poincaré objects. Okay, so let's just also define this translation category of this functor. And then reduce it to Poincaré. Okay. Now I want to explain how this setup gives rise to cobordism categories. And then we can analyze the situation.
So is this Q in the chain complex setting that has a product in the homotopy?
The Q in the chain complex setting, I think I just erased it, was basically the homotopy sequence of this. So it's the symmetric bilinear forms.
Okay.
The spectrum of symmetric bilinear forms. So what is a cobordism between Poincaré objects? And that's very nice. We can just view it as a Poincaré object in some other category. So again, I need to call this Q1C. So this was just a function category from ST1, which is this category C. So something like that. Cospan, and then if C has a quadratic structure, we can canonically define a quadratic structure on here. So have quadratic structure. And there's just a simple formula, it's the limit. So an element, a quadratic structure on such a diagram would be a quadratic structure here, here, and here, and they're compatible. And then you prove that it's Poincaré, it's representable, and defines the duality. And you define a Poincaré object in this category now to be cobordism. So that's quite nice.
By compatible, if that, just in a stupid example, if those are just vector spaces, that would just be isometric embeddings or something? Hard to say. I don't know what compatible means exactly.
Oh, compatible. I mean, okay, I can define the functor for you if this was your question. So we need a functor from this Q1C of. We need the functor spectrum. And we just take the limit. I mean, element in Q1C is a span, and then we apply Q to this, then we get a co-span of the spectrum.
Okay.
And we take the homotopy limit of that. Okay. Okay, so now we can define a cobordism category. But probably doesn't like the term, so he just uses another name for it. People call it Hermitian K-theory. So in n-simplex is the space of Poincaré objects Q n of C, which is cobordism. Okay. So sorry for the place, this is a very structure and it's Q. This is the biggest problem in our paper, we don't try to. So I hope you can. Okay, so this is a complete single space. And this is my right cobordism category. And in particular, this means that two cobordisms we can glue together. And this is already what Ranicki knew how to compose these Poincaré cobordisms. Okay. Now let's try to formulate an analogous theorem of Genauer's theorem in this context. So we can again define null of C. Well, we have already defined it. Subcategory, the category of spans, where one object is trivial. And now it's a matter of fact that this duality on here restricts the duality on here by the restricted quadratic functor. Just show that, and therefore the restricted quadratic functor here is also Poincaré, and we can write down its cobordism category. Now let me start the theorem. Now this is due to all of us here.
That's 8 people.
But
this bracket is C.
C. So first of all, we get a final sequence. Poincaré objects in Q dot. Let me start here writing Poincaré objects in Q dot null C. Of course, dependent on the quadratic structure here. Then we can there's a functor to Q dot C Q. And the homotopy fiber of this functor is Q dot. So these are the null bordisms that are whose boundary is trivial, and in the span case it just said it's just an object. But now we have to be careful with the Poincaré structure because it's an object. But the Poincaré structure comes with two null homotopies because this was defined as a limit and the endpoint of the cobordism is 0. So it's actually in loops of Q. It's like in Genauer's theorem, the dimension shifts by 1. And the fiber sequence. And actually, we can say more on that. We can explicitly say what a Poincaré object in null bordism category is, because I mean the statement is just that C, that's just the span category of C. So null Poincaré null bordism, this cobordism category of that is just the same thing as a Poincaré span category. So maybe the loop space of this is the algebraic K-theory of C. So these Poincaré cobordism categories sit in an extension with the algebraic K-theory. And so maybe it's a good idea to think of this like as a forgetful map, which forgets the quadratic structure. This is a hyperbolic map.
So in particular, it doesn't depend on the quadratic structure.
Yes. We were quite surprised that we came up with this. Okay. So what else is there? So from such a theorem, we can quite formally deduce that this is even loop space of a spectrum, and this has already. I mean, in the span case, this is due to Waldhausen, who writes down a spectrum using the iterative Westphal construction. And in the cobordism category case, this is also true, and it was Bergstedt-Madsen proved this, that you can deloop the cobordism category by iterating cobordism category constructions. So the same is here true. So the space is concrete objects of C, and then now we have to be again careful, maybe with the shifts. So one period object is fused up of C, and then we have to shift the quadratic structure in. So there's a map from here to here, which essentially uses closed manifold as an algorithm or closed object. Algorithm from empty to empty. So this is a map to the loop space of the realization. And we can iterate this. We've got n, C, sigma and q. And this defines is a positive omega spectrum. So the joint structure maps from here to here and to here are all equivalences, and the loop space of this is the loop space of the spectrum. And we call this Rosendiek bit of C, Q.
You have like a four periodicity in that?
And we have a Karoubi periodicity.
Yeah, that's right. Yeah.
Yeah. But it's, I mean,
It doesn't repeat every four.
it doesn't repeat in general. So, I mean, this the homotopy, I mean, is bi-graded, of course. We have like a dimension shift degree and a homotopy degree of the spectrum. And in the algebraic case, so over HC modular spectra, this is 4 periodic in here. This is already what Ranicki used, which makes the L theory of a ring 4 periodic. But it's not periodic. Yeah.
Can you also say something about the first structure map? So
This is something,
completion
we think of this as a group completion, I think, but it's not, but it's something like that. It's like the passage from the groupoid core of category to exhaustion theory. I mean, we can literally write down the same statement for the span categories, and then it's also true, and we see algebraic K-theory.
Some kind of visage theorem in there? Or?
Yeah, not that far, I think. So we have the additivity theorem.
Yeah.
Well, if you know what a visage for stable infinity categories is, that would be great.
Okay, well, that's like homework project.
And we have to generalize that, which is kind
So the stable index is the Cartesian square of spectra. So the GW spectrum I've just defined, this maps to the L theory spectrum. You can define L theory in this context also, which generalizes Ranicki's L theory construction. There's a map like this, and there's also a map from GW in the algebraic K-theory, which takes a Poincaré object and just use the object, which forgets the quadratic structure. But then this object is still self-dual, so we lend actually the homotopy sequence here. And there's a map from here to the text spectrum. And there's a map here, psi, I think. And this is Cartesian. Okay. And this says that could have defined GW just as a product like this. Like
Sorry, what's the L?
It's the L theory of this quadratic of this Poincaré category. So it's a cobordism space. I mean, we have a notion of cobordism, and then we can define L theory, whose homotopy groups are precisely the cobordism groups.
Oh, okay.
In the sense I defined. And depending on what you take as C and Q, of course, I mean, for example, you could get symmetric or quadratic L theory, depending whether you take the symmetric Q or the quadratic Q. And there are even more choices.
Is it also the geometric fixed points?
Oh, yes. So I think, so now we have a spectrum with a C2 action, and a diagram like this always defines a genuine C2 spectrum. And then it's automatically true that it's the fixed points of this genuine C2 spectrum, and this is the geometric fixed points. And so what I find quite surprising is, depending on the choice of Q, you might get just the very same spectrum with C2 action here. For example, the symmetric and the quadratic case. It's the same spectrum here, the same C2 action, so this does not change, but this side changes. So I mean, you get kind of different genuine refinements of the usual spectrum, K-theory spectrum with the prediction, depending on which quadratic structure we chose, so which is the linear extensions of the fixed point thing. Okay, so maybe I should also say something on this map Xi. So this map Xi, or version of it, first appeared in works of Weiss and Williams. So of course they didn't deal with stable infinity categories, but I mean they work with Waldhausen categories with manual Whitehead product. And they wrote down basically by the same formula map Xi like this. And they used this to define something by Kullback, which they call LA theory. And this LA theory actually, I mean, the assembly map for the LA theory completely determines the difference between self-equivalences and self-homeomorphisms of closed manifolds in the concordant stable range. So I find it quite surprising that this GW object kind of appears again. I mean, we don't know it's precisely the same, of course, because we have to compare the settings, but it's quite likely. I mean, that is a version of the LA theory as defined by Weiss and Williams. Okay, then we may wonder actually what is the analogous result of this in the Genauer world. And of course, I don't think there's something like this with the situation, which we always can be maps to. But at least, I mean, this map exists, and it's just the map from the cobordism category to the cobordism space, which on spectra is modeled by the inclusion of suspension MTOD into MO. There's a map like this. It has a whole filtration, and you know what the subquotients are. These are precisely stable infinity things of so sigma infinity of BOD, which is like the homotopy type of the cobordism categories boundary. And this filtration we also get. So this is filtered by cobordism categories. And the filtration quotients are precisely this Genauer type categories with boundaries. So it's quite analogous, except that in the geometric case we don't have a right design. Okay, so I should also say that Schlichting has defined some Additivity theorem in a more algebraic setting. So I think it was like EG categories with weak equivalences and dualities. And this behaves extremely similar to our theory. So the analogous statements of 1, 2, 3 are true, also for Schlichting's theory, when 2 is invertible. And if 2 is invertible, this is not true. And so we might view our theory kind of as a version of Schlichting's theory, which has this nice behavior even when 2 is not invertible.
So I think that the map from the fixed points to the geometric fixed points has always, in the C2 world, always the filtration.
Yes, that's the
And this is the same
This
filtration.
is the filtration. Yeah.
That was a question of certain relations at some point. That got the whole, the 9 authors fused together was the question. Is that the same filtration?
So it was a good question.
Yes.
Okay, and then maybe I can just say, to finish this grid theory also has a universal property, so it's a universal additive invariant on this category cut G. Additive means that it maps split Verdier sequences we have to define into cofiber to fiber sequences. Okay, that's it. Thank you.
Further questions? Tomer.
So can you state precisely the relationship of your general situation to the geometric situation you talked about at the beginning? It's not exactly a special case, right?
No, I think I don't have a context in which both in all 3 situations literally apply. So this would be something like an abstract setting where we can talk about heads and ordisms and stuff. And I don't know this setting. I mean, so, but I mean, just to say what the analogy is, we have here filtration, which is precisely filtration from the general world. And the filtration quotients of this filtration are precisely suspensions of the algebraic K-theory spectrum. And in Genauer setting, and the cobordism category setting, we have a filtration of the cobordism category by the cobordism space, which you can also define with the same methods basically. And the filtration quotients are precisely the cobordism categories with boundaries and suspensions like this.
What about the map? Like, if I look at, I don't know, frame the manifold and I look at the suspension spectrum from that to spectra or something like that, do you think you can?
I mean, there should, of course, I mean, I tried to hint at there should be a map from the geometric cobordism category to this Poincaré cobordism category, which has the manifold with Poincaré complex and cobordism to the Poincaré cobordism. And all this should be compatible with that. But I mean, so far we haven't written down the map, so okay.
Anybody else? All right, then let's thank the speaker.